G'day everybody. Today we're going to look at composite functions. We'll talk about what is a composite function, how do we find values or rules of composite functions. We'll spend a little bit of time just reviewing the definitions of domain and range. That's important for what's coming up when we begin to talk about when a composite function is defined. We'll do a couple of problems together where we find the implied or maximal domain of a composite function. And we might just come back and visit inverse functions and see what they have to do with composite functions. I'm going to represent functions today as machines. So we'll talk about functions f and g for a little while. So imagine that f is some sort of machine. We have an input x and we call the output of that function f of x. And likewise we have another machine does something different to x and its output is g of x. So a composite function where we might take two functions like f and g. And in the first case, we use the output of f as the input for function g. That's what we call a composite function. And when they occur in this order, when x is inputted into f and the output of f is inputted into g, we call that g of f of x. Another notation for that is to use a small o, g of f of x written like this. And over here, if we reverse the order of the functions, it actually creates a different composite function. It's not the same. And in this case, we input x into g first. The output of g becomes the input of f, and we call that f of g of x. And again, we can use the small o, f of g of x. This might not be a new idea to you, so feel free to pause the video and calculate f of g of 2 and g of f of 2. And for each of these we're given two functions, f of x and g of x. G of x is quadratic, f of x is linear. And thirdly, we will look at a more general expression for the two composite functions, f of g and g of f. So pause the video if you wish. Let's have a look at the first two questions. F of g of 2. In this case, if we use x equals 2, g of x shows us that g of 2 is going to be equal to 6. And so we input 6 into the function f. F of 6 is 17. Likewise, for g of f of 2, we need to find f of 2 first. That's 3 times 2 minus 1, which is 5. We use 5 as the input for g, so g of f of 2 is g of 5. And we can see we get a different value, 27. So certainly f of g of 2 and g of f of 2 are not the same thing. Let's have a look at those two composite functions more generally. Here we can actually substitute into the function f the expression for g. So f of g of x, where f of x is 3 times x minus 1. In the place of x we've got the function g, so 3 times x squared plus 2 minus 1. Expanding and simplifying gives us 3x squared plus 5. And for g of f of x, where g of x is x squared plus 2, we're going to replace x with 3x minus 1. So 3x minus 1 all squared plus 2. Again, expanding and simplifying that expression, we get 9x squared minus 6x plus 3. So again, we see the two composite functions are different to each other. So now we've looked at how we calculate values or expressions for composite functions. We're going to spend a bit of time on domain and range. Let's review domain. So I've got three functions here. three different types of functions. They have different domains. This is one way of representing the domain. Along the x-axis, all the values of x for which that a function can be calculated. In other words, for which the function is defined. So for the parabola, we can use any real value for x, indicated by the red line with two arrows either end. Square root functions, such as this one, in this particular case, x minus 2 needs to be 0 or greater, and so the allowable values of x, or the domain for that function, is 2 to infinity, including 2. And the third function, which is a log function, x plus 3 needs to be greater than 0. We can also see in the graph here we've got an asymptote at -3, and you can see the open endpoint for the domain, so the use of the round brackets. So the domain of this function is -3, -3 to infinity, and I've just done a little swap there if you saw that. Range, on the other hand, has to do with the outputs of each function. In terms of a graph, we think about the y values that are included on a graph. And so I've represented the range as sets up the y-axis. So for the parabola, we've got all the y values from -4 included up to infinity. The square root function, which has an endpoint at the coordinates 2, 1. So its range begins at 1 and is infinite. And the range for the log functions with arrows in both directions from negative to a positive infinity, we've got a range of all real numbers. So when we're thinking about the composite function, and we've got functions where the output of one function becomes the input of another, and vice versa, we need to check that what's coming out of one function is part of the allowable input, or the domain, for the second function. That's the key concept here. So a composite function g of f is defined when the range of f is a subset of the domain of g. So that's the meaning of this symbol here. So the range of f, what comes out of the function f, needs to be part of what is allowed to be put into the function g. So the range of f is a subset of the domain of g. And that's the only time when we can say that a composite function is defined. I'm going to end the first part of this video now, and I'll get you to head over to the second video to finish the lesson.